Cool. Cool. All right, so today it's find the minimum in a rotated sorted array. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, array nums equals 0 through 7 might become 4, 5, 6, 7, 0, 1, 2 if rotated 4 times, or 0, 1, 2, 4, 5, 6, 7 if rotated 7 times. Notice that rotating an array, a at 0, a at 1, a at 2, 1 times results in the array of a of n minus 1, a of 0, a of 1, so forth. Given the sorted array nums of unique elements return the minimum element of this array, you must write an algorithm that runs in O log of n time. Okay, just gonna copy that over to IntelliJ. Cool, so as always, the problem, given the sorted rotated array nums of unique elements, return the minimum element of this array. So here's basic setup. We have nums, the array of 0 through 7, and nums2, which is 11, 13, 15, and 17, and then just print the function itself. So we know that the input is going to be nums. All right, and then what we want to do is we want to think about how we're going to approach this, right? Because this has to be done in log of time, we know we're going to be dividing this array up in halves. With that in mind, usually what we're going to do there is we use the midpoint as a pivot, and we're going to be checking left to right. So intuitively, what we're doing is we're setting 3 points. We're going to have a left value, a right value, and a midpoint. And within our array, our left point is 0, our right point is 7, and our midpoint here would be 4. So essentially all we're going to do is we're going to be checking, hey, is my right bigger than my midpoint? And if it is bigger, we know that all the numbers from my midpoint to my right are bigger than midpoint because they're sorted. So we know the number to the right of the mid is bigger than the mid. We know this is bigger than this. We know this is bigger than these two. So from 4 to 7, it's already sorted. And if we know that 7 is bigger than the midpoint, we know all these are bigger, so we don't have to account for these. So from here, what we're going to do is we're going to move our right. We're moving our right to be equal to our midpoint. So that makes it so the array we're actually going to be looking at will be this right here. Right? And then from there, we just keep going. We're going to have a left point equals 0, 0, right equals 4, and then midpoint equals 1. And then same thing. And we're going to keep doing this over and over again until we end up with the left and the right pointing to 0. Right, and now that's in a very straightforward non-rotated. But what if we want to rotate this? Okay, so this one here is rotated. And same as before, we have a left point, which is 4. We have our right, which is 2, and our midpoint, which here is 7. So here when we compare, our midpoint actually be bigger than our right point, right? So in this one, our midpoint is actually bigger than our right. And that leads to 7 being greater than 2. Now, how do we approach this one? Well, we know this is all sorted. So if we know that from our midpoint is bigger than our right point, we know that all these values here are going to be lower than our right point. So instead of moving our right pointer, we're moving our left pointer to be 1 to the right of our midpoint. Why? Well, we already know this number here, our midpoint, is bigger than 2. So we don't need to keep track of this. So we're going to shift it over 1. So that means left is equal to our midpoint plus 1. And that means that the new one we're going to be working with is 0, 1, and 2. And then we just proceed as usual. But what if we have this flipped? Okay, so now what about this case? Where we have our left equaling 5, our right equals 4, and our midpoint equals 0. Okay, what if we have this scenario? Right, so left equals 1, right equals 0, and midpoint will be equal to 5. So in this scenario, we're going to be comparing the values once again. So on this one, right is lower than our midpoint. So because we know these are sorted, we're going to know that the numbers. So in this one, our midpoint is bigger than our right point. So left is going to be equal to m plus 1. So that will be equal to 5 should throw 1. So it'll be 6, 7, and 0. Cool. And then from here, it'll keep reducing until we end up with the left and the right pointer being at 0. Cool. Let's code that out. Cool. We have return 0 just for now to get rid of the error. So we're going to have 2 pointers. We're going to have the left pointer equal to 0, and we'll have the right pointer And we're going to have a right pointer equal to nums.length minus 1, right? We don't want the value of each cell. We want the positions in the array. So what we're going to do here is while my left pointer is less than my right pointer. We do this because we want to keep shrinking our boundaries until we have the overlap. At that point, it's going to be left equals right. Then we're going to create our midpoint because our midpoint will always be shifting. So midpoint will be equal to the left pointer plus the right pointer divided by 2. This will give us the position of our midpoint, not the value itself. So then if the number in the array that my right pointer is pointing to, if that is bigger than the value in the array that my midpoint is pointing to, what we want to do is we want to move the right pointer to be equal to the midpoint. And we do that because if my right pointer is bigger than my midpoint, we know that it's all sorted. So from the midpoint to the right pointer, all those values are bigger than the midpoint. So we don't need any of them. So we're going to decrease our boundary to be from left to the midpoint. And if that's not the case, we're going to move our left pointer to be where our midpoint is, plus 1. Why? Because in the scenario that our right pointer is not bigger than our midpoint, that means that our midpoint is going to be greater than my right pointer. So because it's already sorted, we want to shift our left point 1 to the right of the midpoint, because we already evaluated is the midpoint smaller than my right one, and it's not, it's bigger. So because it's a bigger value and we want the minimum, we don't need to keep track of it, so we're shifting over 1. And then once this loop finally exits, we're going to go ahead and return the number and our left pointer. You can also do nums at right pointer, because it should give us the same value. So I get rid of this. And cool. Let me go ahead and submit this and we'll go from there. Okay, we're back on LeetCode. Let me go ahead and paste in my code. Make sure it's right. Let's zoom in. Cool, and we hit run. Cool, and they all pass. Let's hit submit. Cool. So runtime is 0 milliseconds. This beats 100% of users with Java, and my memory beats 96% of users. Cool. 91% of solutions are 0 second runtime. Cool. So pretty straightforward. If you know how to use, it's pretty straightforward if you understand that a logarithmic algorithm will basically be divided by 2. Well, not so much divided by 2. It'll be reducing the amount of potential candidates by half every single time. So divided by 2. And that's the way you can kind of think about it whenever you see something that says using log in it. And this works only because it's sorted. If this wasn't sorted, we couldn't do any of it. Having the rotation piece, having the actual sorted array rotate a bit, only plays a small twist on actually just a regular sorted list. But I feel it's a pretty good question, and it actually makes you have to think, hey, how to do it logarithmically, or per time, and then how to actually account for the actual shift in the starting positions of the sorted array. But cool.